Hello, everyone. My name is Arthur Giuliani, and I'm going to be presenting a talk that I gave at the Psychedelic Science Conference last summer in Denver. The title of the talk is A Simple Machine Learning Perspective on Psychedelics and Neuroplasticity. Now, it's pretty well known from either personal experience, anecdotal evidence, or the increasing body of research, clinical research, that psychedelics are capable of helping people overcome various forms of psychological difficulty. And different fields have different ways of approaching this. Neuroscientists have their own way of understanding this, psychiatrists have their own. Likewise, shamans or spiritualists might have their own ways of understanding why this happens. In this talk, we're going to take a unique perspective and try to understand from a machine learning theory perspective what might be going on in the brain and in the mind that allows psychedelics to help people. In order to do this, we're going to be using a simple recurrent neural network model of the brain. Now, this is definitely a toy model and it's very abstracted, but I think it captures the essence of what we're interested in understanding here. So in this simple recurrent neural network model, the brain, it has some sensory input that it receives X. It has some motor output, Y. So in this case, maybe the brain looks at a duck and reports that it sees a duck. And so what might be going on inside the brain? We're going to say that all of the neurons, their pattern of connectivity between each other, we're going to refer to that as the synaptic weights. And then this pattern of activity is going to, at every moment, determine the pattern of neural activity. And this neural activity is what's ultimately then going to update itself over time and be responsible for the actual motor output. What I just described was a kind of like functional description of what this recurrent neural network model is doing. Now, the bigger question is, how does this model actually change, update, learn over time? And to understand that, we're going to draw on one of the more popular theories in computational neuroscience, the theory of predictive processing. And so this theory says that the goal of the brain, as it learns and updates its synaptic weights and neural activity, is to minimize prediction errors. And so prediction errors are going to be the discrepancies between what the brain might predict is about to happen and what actually happens over as many spatial and temporal scales as it can. Now we can begin to make this a little bit more concrete by considering how the neural activity might evolve over time during the task of perception. And to do that, we're going to use what is referred to as an energy function or an energy landscape to understand this. And so that's represented with a very simple 2D diagram in the middle here. And so with an energy function, we can understand that the states of the system are going to be evolving in such a way as to reach lower and lower levels of energy. In this case, that's going to correspond to lower prediction error as well. So in the case of looking at a duck, the system is going to move from a state of not knowing what it's seeing to a state of seeing a duck and being able to report that. So there are energy functions that correspond both to neural activity, like we just looked at, but we can also consider energy functions that correspond to the way in which the synaptic weights, the neural connectivity itself, evolves over time. And so the interesting thing here is that at every specific point in the energy function for the synaptic weights is actually going to correspond itself to an entire energy function for the way in which the neural activity evolves over time. To make this a little more concrete, we can consider again the example of the duck. So say we have a child that's very early in life and hasn't learned to distinguish between different kinds of birds. So when it sees a duck, all it can possibly know or say is bird. And so that's represented in the upper right-hand corner. Then as the child learns more about different kinds of animals, it's going to be able to distinguish between, let's say, ducks and chickens. And this is a lower energy state because being able to specify a duck is going to allow it to predict more things about what the duck is going to look like, how the duck is going to act, and therefore reduce prediction error. And so that's why it's a lower state. Now, what we've been considering thus far are stimuli that are relatively clear-cut. but what if there's an ambiguous stimuli that the system is presented with? And so we have on the left an image of the famous rabbit-duck illusion introduced by Ludwig Wittgenstein, the famous philosopher at the beginning of the 20th century. So what's interesting about this image is, as the name suggests, depending on how you look at it, you can perceive it as being either corresponding to a rabbit or a duck. And this is going to induce a particular kind of energy function for neural activity in which there are multiple lower states or attractors that the system could possibly enter into. And so this might correspond to seeing a rabbit at first and then maybe a duck afterwards, oscillating between the two. What I just described is kind of the basics of how we can think about how the brain might learn using energy functions. Now we're going to get into the more concrete example of what psychedelics might have to do with this and how psychopathology might manifest itself in the model that we're considering. And to do that, we're going to use a very simple parable story about this woman named Sarah. And it's all totally made up. And it doesn't really correspond to reality, but I think it captures all of the core elements of what we're interested in thinking about here. To begin the story, Sarah was born in a remote village by a lake, and this lake is in the middle of a population of a popular migration path for ducks. And so Sarah grew up seeing thousands of ducks as a child. And so all of these ducks and everything Sarah sees is the data distribution that her brain is exposed to during the initial learning process. And this, of course, is going to condition how the neural activity and the synaptic weights evolve over time. So if we take Sarah, who grew up in this environment, and we show her the rabbit-duck illusion, what are we going to find? So in this case, it is the case that she is going to be more likely to see a duck. And this is because she's seen so many ducks, and she has now a kind of like bias towards perceiving ducks. And that's going to manifest as the duck state being the attractor with lower energy. Now, if we look at the synaptic weights, we can kind of better understand how we got to this point. So maybe when Sarah was a child, her neural activity hadn't yet become biased towards seeing ducks. And that might be represented by the image in the upper right here, where the prior over what she might see is kind of equal between the two, or relatively close. Then over time, because the environment has so many ducks, it's actually adaptive for her to become biased towards seeing ducks, because that's more likely to minimize prediction error. And so that becomes the lower energy state for the synaptic weights in this environment. And then what ends up getting instantiated is a prior over neural activity in which the duck attractor has lower energy. And we can kind of break this down into a simple equation here, where we might start with a stimuli that is kind of from a God's eye view ambiguous, this rabbit-duck illusion. Then we have the prior over the beliefs that Sarah has. This is what she brings to the situation. Even in the absence of any stimuli, she's inclined to see a duck. And then these two things together end up producing the posterior, or the actual kind of like realized experience that she might have, how her neural activity might evolve over time. To continue with our story, as an adult, Sarah moves to the city for a promising job. At first, things go well, but she soon finds that she keeps mistaking small duck-sized animals for ducks. And so clearly this isn't great. But what's happened is that there has been a distribution shift. She went from an environment in which there was a specific distribution of stimuli that she was exposed to, ducks all the time, to an environment in which that's no longer the case. So there's a mismatch. And what she finds now is that when, for example, she perceives a rabbit in a park in the city, the neural activity pattern that gets instantiated, the energy function, is actually going to give equal weight to rabbits and ducks. So she finds that half of the time, let's say, she's accidentally perceiving the rabbit as a duck. And in machine learning language, we're going to say that she's overfit to her initial lake environment. And she's overfit because now there are new prediction errors being introduced that weren't there previously. If she had only overfit, we might hope that the brain would be able to update itself, the synaptic weights would change over time, and she'd adapt to the new environment. Now, under ideal conditions, this is what would happen, but many times this isn't the case. What can happen instead is a phenomenon called plasticity loss. And what that looks like concretely with our energy functions is that whereas you would want to start from a state of higher energy and move to a state of lower energy, sometimes there isn't actually a clear path between those two things. So if you stay in a single environment, it's often the case that you might be able to move to that from a state of high energy to low energy, like she did as a child in the lake environment, learning to be biased towards seeing ducks. But then when she moves into the city environment, there's a mismatch. Her synaptic weights haven't changed, but the environment has dramatically changed. And so to get to that unbiased state, there now isn't a direct path, as you can see on the image on the right, from the higher energy attractor to the lower energy attractor. So what we're going to say then is that because of Sarah's secluded life in the lake, her neural activity has become overfit. Her synaptic weights also suffer plasticity loss. And in the context of psychiatry and computational neuroscience, the combination of these two things is referred to as canalization. And this was a term originally developed by Dr. Robin Carhart Harris and his collaborators to describe a number of states of psychopathology that emerge with this pattern. Continuing with our story, Sarah, because she's distressed about seeing ducks, she visits a psychotherapist. And the psychotherapist thinks they understand what's happening. They have a good grasp on canalization. And so they recommend psychedelic-assisted therapy. A couple of weeks later, Sarah is administered psilocybin in a controlled setting with a window looking out onto a meadow. And as she looks out into this meadow, she finds that there are a number of rabbits hopping around on the grass. The question becomes, what does she perceive when she looks out? To answer that, we have to first think about what might be happening in her brain. So one of the major theories about what psychedelics do to these energy functions in the brain is that they relax them. And what that is going to look like is Sarah's neural activity bias going from the diagram on the left to the diagram on the right, where there's a kind of flattening that happens, and the two attractor states, rabbit and duck, end up having relatively equal priority. Now, that's the prior. But when we combine that with the actual evidence, the stimuli of a rabbit, that's very clearly a rabbit, what ends up happening is then that the neural activity that she actually has, the energy function that gets instantiated, is now going to be biased towards rabbit. And this is correct, and she's able to see a rabbit without misperceiving it as a duck, to her great relief. So Sarah goes home after this therapy session, and over the course of the weeks, she finds herself seeing fewer and fewer ducks when they aren't there. What's happening during this period is that her brain is more neuroplastic, and not only has the neural activity changed, but the underlying synaptic weights themselves have begun to change. So we can understand the synaptic weights also as undergoing a kind of flattening and relaxation. So whereas before it was impossible for Sarah's synaptic weights to move from the point of being duck biased to being unbiased because they had developed plasticity loss, after psilocybin, with increased neuroplasticity, it's now possible for those synaptic weights to move to that optimal state of lower energy. And that's our parable of Sarah. It's admittedly a bit silly. Most people don't suffer from seeing ducks when they aren't there, but this concept of energy functions becoming overfit and suffering plasticity loss can apply to a variety of beliefs that are in fact more core to human psychopathology, such as beliefs about oneself, the safety of others, one's body image, what the world is like. And these often then end up manifesting as depression, anxiety, OCD, addiction, and other psychological disorders. And what we've looked at here is the ways in which psychedelics, at least hypothetically, and in these theoretical models, are able to undo overfitting and plasticity loss. What's interesting is that in addition to psychedelics being able to do this, there's emerging research suggesting that meditation and high-quality psychotherapy function in a similar way by undoing these two things and reducing canalization. So this is quite interesting to me, at least, because it points to a potential shared mechanism underlying a number of forms of different psychopathology, as well as a shared mechanism by which mental wellness and healing can take place by reducing it. That's the talk. Thank you so much for listening and taking a look at it. If you want to know more about some of the research that I was citing here and read the papers yourself, there's a link here that links both to the research and work that I've done with my colleagues and some of the work that we cite and build upon. Again, thank you so much.